Hi everybody, I hope this video helps you guys to understand jet noise and how to solve the problem in Ansys. So before I start, I genuinely urge you guys to build a sound theoretical knowledge on jet aeroacoustics, light hill theory, Morrison facet paper. Hi, and I would like to add that the computer doesn't quite integrate well with, so I'm just gonna hop on the workbench for now. And I also like to say on the analysis systems there's no options for fluent, so I'm just gonna open geometry. Here it is, geometry. Let's just wait for it to be opened. Yep, let's do in meters and let's do a sketch. Let's do a sketch in XY plane. So basically I'm gonna sketch a nozzle first of a length of 1 meters, a horizontal length of 1 meters, and a radius of 0.5 meters. So in this case you can change the dimensions according to your needs, and according to the thickness of your nozzle as well. In this case the thickness for the blunt end is, I'm just gonna keep it up to 0.1 meters. Yep, now all the dimensions are done. I need to click on the create and revolve. I'm going to revolve it around the x-axis denoted by the red arrow. So generate. So here it is, the solid nozzle. Yeah, it is quite quick and fairly simple to make a circular nozzle here in Ansys, and I would suggest to you to import the complex shapes. But now I'm gonna freeze the solid, so it helps us to cut the material later on. So now I'm gonna make another sketch on the same XY plane. Yep. So I'm gonna make a rectangular control volume. So I would suggest that the sidewalls, the sidewalls, the further they are from the action area is much better, because in real life situations there's basically no walls. So for this case I'm just gonna say 10 meters on either directions from the nozzle. The most important bit is the flow away from the nozzle, and for that case I'm gonna put it down 30 meters. So now all the dimensions are being set. What I want to do is now extrude the rectangular shape. So I'm gonna extrude it symmetrically. You are symmetrically on both sides here, and I'm gonna give a length of 10 meters, so it's fairly big and good enough. I guess. So now it is the time to cut the frozen material. So now I have to separate to the previous body from the other one, the frozen body from the solid body. So I clicked on the cut material and click on the solid body and generate. So here you are. The emptiness is the space, is the cut part left by the frozen body. So basically that is the cut operation. And after that I'm just gonna save the geometry that I've just made. And I'm gonna link the geometry so that I can work on the mesh. And let me just open the mesh now. It's gonna take a while to load up. Here we are, and I just clicked on generate mesh without doing anything. Just click on generate mesh and it gives you a fairly okay mesh. I mean, it's big, you don't want it. So what I'm gonna do is change the settings, change the sizing from coarse to fine. So after I do that, you can significantly see the decrease in mesh width. And as you can see at the inlet, you want more mesh, but for this case it's okay. And I'm gonna name the nozzle as the inlet. I'm gonna name the sides, shown by the green, as walls. Let me just name it. Here it is. And yeah, so what I need to do, the so now I'm gonna open Fluent. As I told before, to do separately because the workstation and the workbench doesn't quite integrate with this computer. So I'm gonna select double precision and obviously a 3D. So here we are on the Ansys Fluent, and let me open a mesh file. So as I've already done the mesh, I can just open it. A file, mesh file. So here it is. So the red ones, and the red one is the outlet. The white walls are the white are the walls, and the blue one, the tiny blue one, is the inlet for this simulation. So now I'm gonna do the problem setup. This is a pressure-based problem, and the model it is gonna be K epsilon, but we do have inviscid, laminar, and other options as well. So, but the Tam and Auriault's formula, if you remember, depends on K epsilon model. So here we can either choose realizable or standard. I'm just choosing standard, and I'm just keeping the values as they are, the default ones. So with all the default values, but you have to choose the K epsilon model, and yep, the nozzle is aluminum, and for the inlet flow, I've choose the flow directions from x-axis to be 303.56 meter per second, which represents a Mach number of 0.9. So let me just close that, and from the outlet, so from the walls, you can either choose your one shear value, or you can just use the no slip condition. It's up to you. So I'm just going to use the no slip condition. Okay, and I'm going to compute from inlet. Obviously, the solution methods is the important bit. Scheme, just simple scheme, and basically the first order of point. The first order of point are less accurate, but they are more faster than second order of point. And the solution control you can choose as you want. The hybrid standard initialization. Standard initialization, you initialize from inlet and click on the initialize button. After that, to run the calculation, you need to specify the iterations and the time steps. I'm just going to do 20 iterations because this is a very big control volume. It has to be said. The mesh is quite big, and the meshes are fine, and it's going to take a while. So just let's just wait for this to be converged. I mean, it's not going to converge, but it's going to stop at 20 iterations. For conversions, it's going to take like 1 hour and about 700 to 800 iterations to converge. So basically, it's not going to converge in 20 iterations, to be honest, but how you should do it. So after you're done the first order or point order, you can basically change it to second order to increase the accuracy. And from the figure above, you can see the x velocity, y velocity, z velocity, and the continuity. So basically they just tell you about the convergence properties of the solution that you are currently simulating. So the closer they are, is more likely that you have got a more convergent solution. As you can see that from this graph, it's not quite converged. There are quite spaces between those curves, and yeah, what you can do is increase the number of iterations, or you can go to solution methods and change to second order of point, which is more accurate but obviously takes longer. And you can also increase just initialize from inlet, and okay, and you can just increase the number of iterations, and you can calculate. So I'm not gonna do 1 hour of simulation here, and yep, that's the end of